Welcome to Dreaming Through Knowledge. Tonight, we drift with wings and wind, across silver clouds and gentle altitudes, to explore how airplanes fly. If you enjoy these journeys, please follow the channel and share what you'd like to uncover next. When I look to the sky and watch a plane vanish on the horizon, I think of one simple word: wonder. How does such a heavy machine lift its nose, climb into the blue, and slice through the air? In this moment, I invite you to settle back, let your breathing slow, and trace the journey of human flight, from the first dreamers who looked up to the silent laws of lift that carry us on wings. Long before engines and runways, people looked at birds and clouds and wished they could rise. They crafted kites, gliders, and even wings made of wood and fabric. In the hush of morning light they ran until the air lifted them. Some soared, some fell, but each attempt carried hope. That hope became the blueprint of flight. From that leap into the sky, the science followed. Engineers and dreamers asked, what lets an airplane stay up? How do wings work? How do engines push? How does a heavy frame glide like a feather on the breeze? And the answer lies in invisible forces around us. When I pass under a jet's contrail, I feel connected to that quest. The pursuit of lift and thrust, of balance and motion. Modern airplanes weigh tens of thousands of kilograms, carry hundreds of passengers, yet once airborne, they seem to float. The key is that four fundamental forces play together. Scientists call them lift, weight, thrust, and drag. Lift is the gentle push that raises the airplane upward, against the pull of Earth. Weight is that pull, the constant tug downward we all feel. Thrust is the forward push of engines, and drag is the resistance of air, the invisible brake. When lift and thrust win, the airplane climbs. When weight or drag overpower, it descends. I like to picture a wing slicing through air. The top surface of the wing makes the air travel faster than the air beneath. Faster air means lower pressure above the wing. The pressure beneath remains higher, so the wing rises. It is a quiet law of nature. Yet that explanation, though elegant, does not tell the whole story. A more complete view also recognizes the action of the wing redirecting air downward. The wing pushes air down, and the equal and opposite reaction pushes the wing up. Newton's third law in motion. When I think of that, I imagine a bird throwing air downwards with its wingtip, and the air responding by lifting the bird. The airplane does the same, only the wing is shaped, solid, and guided by pilots and computers. The invisible dance between air and wing becomes visible only in flight. The shape of the wing matters deeply. The aerofoil is curved with purpose. Engineers design it so that the air flows gracefully, so the wing stays steady and the aircraft remains calm. They reduce drag by smoothing surfaces, by tapering edges, by controlling the wake behind the plane. Imagine now the runway ahead, the engines spooling, the thrust pushing the airplane forward. The forward motion is the beginning of the act of flight. Without motion, there is no lift, no climb, no glide. The plane accelerates. The airflow over the wing gains speed, the lift rises, and the plane becomes airborne. When I stare at that moment of takeoff, I feel the human longing embedded in every engine roar, every rolling wheel, every ascending frame. To rise is to transcend gravity for a moment, to leave the ground and look back at the world from a new height. Above us, the clouds wait. The plane passes through them or over them and ascends into clear sky, into thinner air, where the wings must work differently. The designers account for altitude, pressure, temperature, wind. Every flight is also a negotiation with nature. Quieter? The answers often came from nature. And as you drift deeper into sleep, know that every flight you've taken is part of a continuum. Human desire, science, courage, movement. The next time you hear the low rumble of engines, you will be hearing that long story of lift and motion unfolding in that moment. In ancient civilizations, flight was more a dream than a discipline. The myths of Icarus and Daedalus in Greece, and the feathered dragons and kites of early China, reflected humanity's fascination with air and freedom. Kites, developed more than 2,000 years ago, became the first controllable structures to fly. Their success hinted that air was not empty, but a substance that could be shaped and used. By the Renaissance, curiosity about air had become systematic. Leonardo da Vinci studied the motion of birds and proposed machines that could imitate their flight. His sketches showed gliders, parachutes, and rotating wings, all grounded in close observation. Though none were built successfully in his lifetime, his notes reveal the first recognition that flight depended on balance, lift, and the flow of air around a surface. In the early 19th century, engineers began to test those ideas with real machines. Sir George Cayley, an English inventor, was among the first to identify the four forces that govern flight: lift, weight, thrust, and drag. He discovered that curved wings generated more lift than flat ones, and that a tail could stabilize the craft. His designs marked the transition from dream to engineering. Otto Lilienthal, working later in Germany, expanded that knowledge through direct experiment. He built gliders with wings modeled on storks and gulls, recording every flight and failure. Lilienthal's studies of wing curvature proved that the flow of air over a cambered surface produced measurable lift. His careful documentation transformed flight from art into data. In 1896, Lilienthal was killed during one of his experiments, but his work reached far beyond his time. His data influenced a new generation of inventors, including two brothers from Dayton, Ohio, Wilbur and Orville Wright. The Wright brothers approached flight as a problem of control. Earlier, gliders could rise, but they could not remain stable. The brothers observed that birds constantly twisted their wings to maintain balance, and they sought to replicate that motion mechanically. Their solution was wing warping, a system that allowed the pilot to twist the wingtips in opposite directions, adjusting lift on each side. Before building their powered craft, the Wrights conducted hundreds of tests. They constructed a small wind tunnel to study how air moved around different wing shapes. Their measurements revealed that many accepted aerodynamic formulas were inaccurate. With new data, they designed wings that generated predictable lift and propellers that acted as rotating airfoils. On December 17, 1903, their flyer made its first sustained flight at Kitty Hawk, North Carolina. It lasted only 12 seconds and covered 37 meters, but it proved that powered, controlled, human flight was possible. The brothers had solved the fundamental problems of lift, propulsion, and stability in a single design. In the following years, aviation developed rapidly. Engineers refined airfoil shapes, improved materials, and studied airflow in controlled environments. Lift and drag were now understood as measurable effects of pressure and velocity. Airplanes grew larger and more efficient, each generation learning from the one before it. During the First World War, the airplane became an essential tool. The need for faster, more reliable machines drove innovation in engine design and structural strength. Airframes of wood and fabric evolved into metal constructions. The principles of control, elevator, rudder, and aileron, became standardized, allowing pilots to manage all three axes of flight: pitch, yaw, and roll. Between the wars, flight moved from military application to public life. Airmail and passenger service connected cities for the first time. Pilots crossed oceans and mountain ranges once thought impassable. Aviation schools taught the science of lift, drag, and engine performance. The airplane had become not just a machine of exploration, but a new form of transportation. By the 1930s, aerodynamic theory had matured. Engineers understood that lift depended not only on wing shape, but also on the speed and density of the surrounding air. Streamlined fuselages and retractable landing gear reduced drag. Metal wings could withstand greater forces, allowing for longer and higher flights. The next great leap came with the jet engine. Instead of turning a propeller, jets compressed and ignited air directly, producing continuous thrust. The first operational jet aircraft appeared in the 1940s, reaching speeds beyond 500 miles per hour. The balance of the four forces remained the same, but the power driving them had changed. From that point, the science of flight expanded outward, higher, faster, farther. Supersonic travel required new understanding of shock waves and air compression. Engineers studied how air behaves at different speeds and altitudes, mapping the boundaries of performance. The same principles that lifted gliders into the air now carried spacecraft toward orbit. The story of flight is also a story of observation. Every major breakthrough has come from watching nature closely. How birds tilt their wings, how air flows around obstacles, how balance and movement work together. Modern wings still follow the same patterns found in feathers and fins. The quiet order of nature remains the model for flight. Each airplane flying today, from small trainers to intercontinental jets, relies on the same foundation discovered over a century ago. Air moves faster over a curved surface, reducing pressure above the wing. The difference in pressure creates lift. Thrust moves the craft forward. Drag and weight pull it back. Flight is the steady balance between those four forces. From early myths to modern engines, the path has always been guided by the same principle: understanding air as a physical substance that can be shaped, directed, and trusted. The sky is not an enemy to be conquered, but a medium to be learned. The science that began with sketches and gliders now sustains a world connected by air. What once took weeks to cross can be reached in hours. Flight has become part of daily life, a quiet collaboration between the laws of physics and human design. The next part of this journey explores those laws more closely: how air behaves when it meets a wing, how pressure, speed, and angle combine to create lift, and how this invisible balance keeps every airplane in the sky. Airplanes remain in the sky because of the forces that act upon them. Though these forces are invisible, they are constant and measurable. Every second of flight depends on their balance. 4 primary forces govern flight. Lift acts upward, opposing the pull of gravity. Weight, caused by gravity, pulls downward. Thrust moves the airplane forward and drag resists that motion. When lift equals weight and thrust equals drag, the airplane maintains steady flight. Lift begins with the behavior of air. Air is made of countless molecules that move in all directions. When an airplane moves forward, the wings meet those molecules and change their motion. The shape of the wing determines how the air reacts. Most airplane wings are curved on top and flatter underneath. This shape is called an airfoil. As air flows over the curved upper surface, it must travel a longer path in the same amount of time as the air moving below. The air above therefore moves faster, and according to Bernoulli's principle, faster moving air creates lower pressure. The higher pressure beneath the wing pushes upward, producing lift. This explanation is only part of the story. The wing also pushes air downward as it moves forward. Newton's third law of motion states that every action produces an equal and opposite reaction. As the wing forces air downward, the air pushes the wing upward. Both Bernoulli's and Newton's principles describe the same process: air flowing, pressure changing, forces reacting. Lift also depends on the angle at which the wing meets the oncoming air, called the angle of attack. At small angles, air flows smoothly over the surface, and lift increases steadily. Beyond a critical angle, the flow separates from the top of the wing, creating turbulence and a sudden loss of lift. This is known as a stall. Understanding that limit is essential for safe flight. Air itself plays a crucial role. It behaves differently depending on altitude, temperature, and speed. Near sea level, air is dense, containing more molecules per volume. At higher altitudes, it becomes thinner, providing less lift for the same wing area and speed. This is why aircraft must travel faster or use larger wings when flying at high altitudes. The atmosphere also affects engine performance. Jet engines rely on the compression of air before ignition. At high altitudes, less air enters the engine, so modern designs use compressors and fans to maintain pressure and efficiency. Flight is a continuous balance between the airplane and the environment it moves through. Lift is always accompanied by drag, the force that resists motion through air. Drag appears in several forms. Parasitic drag comes from friction between air and the surface of the airplane. It increases with speed. Induced drag is a byproduct of lift itself. As air moves from the high-pressure area beneath the wing to the low-pressure area above, it curls into spirals at the wingtips, creating vortices. These swirling trails consume energy and slow the airplane slightly. To reduce drag, engineers shape wings and fuselages with smooth, tapered profiles. Modern aircraft often use winglets, small, vertical fins at the tips of the wings, to control the vortices and improve efficiency. Even small changes in surface texture can make a difference. Reducing drag by just 1% can save thousands of liters of fuel on long flights. Thrust, the forward force, is produced by engines. In propeller-driven aircraft, thrust comes from blades that act like rotating wings, creating pressure differences between their front and back surfaces. In jet aircraft, air is drawn into an engine, compressed, mixed with fuel, and ignited. The high-speed exhaust pushes backward, creating a forward reaction. Both types rely on the same fundamental principle: acceleration of air in one direction to create motion in the opposite direction. The combination of lift, drag, weight, and thrust defines every moment of flight. During takeoff, thrust and lift must exceed drag and weight. During cruising, they are held in equilibrium. During landing, lift and thrust are reduced in a controlled way, allowing gravity to return the airplane safely to the ground. Engineers often visualize these relationships using diagrams of force vectors. Each vector represents magnitude and direction. The goal of stable flight is to keep the total of these vectors balanced around the airplane's center of gravity. If lift shifts too far behind that point, the plane becomes unstable. If thrust or drag become unbalanced, altitude or speed will change. Modern flight computers constantly monitor these variables, adjusting control surfaces to maintain equilibrium. Air around a moving airplane does not flow in straight lines. It bends and accelerates, forming patterns of pressure and turbulence. The thin layer of air closest to the surface of the wing, called the boundary layer, is especially important. Within this layer, friction slows the air. If the layer remains smooth and attached, the wing is efficient. If it separates, drag increases sharply. Designers spend years studying how to manage this boundary layer. Polished surfaces, laminar flow airfoils, and microscopic textures all help keep the air attached longer. Even the smallest irregularity can disturb the flow. The smoother the surface, the more graceful the flight. Nature demonstrates these same principles. The feathers of birds reduce turbulence in flight. The scales of fish guide water along their bodies with minimal drag. Engineers often look to these patterns for inspiration. The study of such natural efficiency is known as biomimicry, and it continues to influence aviation design. The study of airflow is called aerodynamics, literally the motion of air. In wind tunnels, scientists visualize air using smoke or lasers to reveal its paths around wings and fuselages. These experiments show the flow dividing cleanly at the leading edge, accelerating over the top, and rejoining smoothly at the trailing edge. When that pattern holds, lift is strong and stable. When the flow breaks apart, turbulence appears, and control becomes more difficult. Airplanes are designed to manage these conditions automatically. Slats and flaps along the wing's edges can extend during takeoff and landing to increase surface area and lift at slower speeds. Spoilers rise to reduce lift and increase drag when descending. Every surface on a wing has a role in controlling the relationship between airflow and pressure. At cruising altitude, typically around 35,000 feet, the balance of forces reaches a steady state. The engines provide just enough thrust to overcome drag, and the wings generate just enough lift to support the airplane's weight. In this state, flight becomes almost silent and efficient, sustained by the continuous motion of air. The science of lift may seem abstract, but it is also profoundly natural. Every gliding bird, every drifting seed, and every wave of wind across a mountain follows the same laws. The airplane does not fight against nature. It works within it, using physics that have always existed in the air around us. In the next part of this story, the focus turns to the act of flying itself, how pilots interpret instruments, navigate the invisible sky, and keep balance amid air that is always moving. Every flight begins long before the airplane leaves the ground. Pilots and engineers prepare for hours, studying weather patterns, air pressure, and routes that cross invisible highways in the sky. Air travel may appear effortless, but each journey is the result of precision, coordination, and trust in physics. A pilot's main task is to maintain balance between the four forces of flight: lift, weight, thrust, and drag. The airplane is stable only when those forces are in harmony. Controlling that balance requires constant awareness. Even in calm air, conditions shift. Temperature changes, wind direction varies, and air density fluctuates. The control of an airplane relies on three axes of motion. Pitch moves the nose up or down. Roll tilts the wings side to side, and yaw turns the airplane left or right. Each axis passes through the center of gravity, and each is governed by specific control surfaces on the wings and tail. The elevator, located on the horizontal tail, controls pitch. When it tilts upward, it pushes the tail down and the nose rises, increasing lift on the wings. When it tilts downward, the tail rises and the nose lowers. The ailerons, small hinged panels near the wingtips, control roll. When one moves up and the other moves down, one wing generates more lift than the other, causing the airplane to bank gently. The rudder, mounted on the vertical tail, controls yaw by redirecting the flow of air left or right. These movements work together. A coordinated turn, for example, uses all three controls: ailerons to roll, rudder to align the nose, and elevator to maintain altitude. The pilot must sense how each surface affects the others. In modern aircraft, computers assist with this coordination, but the principles remain the same. Most large airplanes now use fly-by-wire systems. Instead of direct mechanical cables connecting the pilot's controls to the surfaces, electrical signals carry the commands. Sensors and processors interpret these signals, adjusting them to maintain stability. This allows the aircraft to respond more precisely and to correct small disturbances automatically. Inside the cockpit, dozens of instruments translate the invisible world outside into measurable information. The altimeter measures altitude through changes in air pressure. The airspeed indicator shows how quickly the plane moves through the air. The artificial horizon, or attitude indicator, displays the airplane's orientation relative to Earth, a vital reference when clouds hide the real horizon. Gyroscopes and accelerometers feed data to flight computers. The pilot monitors engine performance through gauges showing temperature, pressure, and fuel flow. Navigation screens display the airplane's position using global satellite signals, combined with data from onboard sensors. The cockpit is both a laboratory and a sanctuary of motion, where science becomes daily practice. Navigation has evolved from simple visual cues to systems of extraordinary precision. Early pilots followed rivers, railways, or landmarks. Today, aircraft move along established airways, three-dimensional routes defined by coordinates, beacons, and altitude levels. Air traffic control ensures that each airplane maintains safe distance and altitude, guiding them through layers of sky invisible to the eye. Communication is constant. Pilots speak with controllers at each stage of the journey: ground, tower, departure, en route, and approach. Every instruction is clear, concise, and standardized, reducing the chance of misunderstanding. Above 10,000 meters, in thin, cold air, voices still pass through radio waves, keeping every aircraft connected in the vast network of flight. Weather plays a central role in every decision. The atmosphere is never still. It shifts and breathes. Pilots read weather charts that map temperature, wind speed, turbulence, and cloud formations. Instruments measure airspeed relative to the surrounding air mass, not to the ground. A strong headwind can slow progress. A tailwind can shorten a journey by hundreds of kilometers. Clouds and storms bring special challenges. In towering cumulonimbus formations, updrafts and lightning can endanger even large aircraft. Modern weather radar detects these systems long before they are visible, allowing the flight path to curve smoothly around them. The goal is not to resist the atmosphere, but to move within it safely. At high altitude, air traffic follows specific corridors separated by height. Commercial flights typically cruise between 9 and 12 kilometers above sea level, where air resistance is low and fuel efficiency is highest. The autopilot manages heading, altitude, and speed, freeing pilots to monitor systems and plan for descent. Autopilot systems do not replace pilots. They extend their ability to maintain stability over long periods. A pilot sets the desired altitude and speed, and the computer continuously adjusts the control surfaces and engine output to hold them steady. If conditions change, a shift in wind, or a change in temperature, the pilot can override or update the settings instantly. Guidance from satellites has revolutionized navigation. The Global Positioning System, or GPS, uses signals from at least 4 satellites to determine an aircraft's position with accuracy within meters. Combined with onboard inertial systems, this allows airplanes to fly precise routes even over oceans or deserts where no landmarks exist. Every takeoff and landing, however, still depends on direct human judgment. During takeoff, pilots monitor speed closely. When the aircraft reaches a calculated velocity known as V1, it must leave the ground. Below that speed, it can still stop safely if needed. Seconds later, at rotation speed, the pilot pulls back gently on the control column, lifting the nose as lift overcomes weight. Landing is the reverse process. The airplane descends along a fixed path called the glide slope. Pilots adjust power, extend flaps, and deploy landing gear. As the aircraft nears the runway, ground effect, a cushion of higher pressure beneath the wings, softens the descent. Wheels meet the surface, and thrust reversers or brakes bring the airplane to a slow, even stop. Safety in aviation relies on systems designed with redundancy. Critical components such as engines, power sources, and flight controls have backups. Modern commercial aviation is among the safest forms of travel ever created. Each procedure, from fueling to descent, follows precise standards learned through decades of experience and research. Pilots undergo continuous training to maintain awareness of every scenario: turbulence, instrument failure, or sudden weather changes. Simulators reproduce these conditions with astonishing realism. In them, pilots practice responses until the correct actions become instinct. The goal is not perfection, but preparedness. Flying an airplane requires technical knowledge, but also trust in the machine, in physics, and in teamwork. Each flight connects engineers, air traffic controllers, maintenance crews, and meteorologists. Together, they form an invisible chain that stretches from the ground to the upper atmosphere. To most passengers, the experience of flight feels simple: a smooth ascent, a quiet cruise, a gentle landing. Behind that calm lies constant calculation. Every moment is measured in speed, angle, and altitude. The airplane is both a physical object and a continuous process. Thousands of adjustments guided by invisible air. Inside the cabin, that complexity fades. The hum of engines becomes steady, the air pressure stabilizes, and the world outside turns to pale blue. What feels peaceful is, in fact, a perfect equilibrium, sustained by human skill and scientific understanding. The science of flight is not only mechanical, it is also deeply human. It represents the union of observation, learning, and coordination. From the earliest gliders to modern jets, the goal has remained the same: to move through air safely, efficiently, and beautifully. In the next part of our journey, the focus turns upward, toward the atmosphere itself, the layers of air that shape every flight, the currents that guide weather and wind, and the delicate environment through which all airplanes travel. Above the ground, the sky is not empty. It is a layered structure of gases, pressure, and motion, a living system that shapes every flight. Airplanes do not travel through space, but through this moving ocean of air. Understanding its structure is essential for safe and efficient flight. Earth's atmosphere extends outward for more than 100 kilometers. It contains several layers, each with its own characteristics. Closest to the ground lies the troposphere, stretching roughly 12 kilometers upward. This is where weather occurs, and where almost all commercial flights take place. In the troposphere, temperature decreases steadily with altitude. Warm air near the surface rises, cools, and descends again, creating currents and clouds. The motion of these air masses produces wind. Mountains, oceans, and seasons shape their patterns, forming the turbulence and smooth air that pilots encounter every day. Above the troposphere lies the stratosphere, a calm and stable layer that begins at about 12 kilometers and reaches up to 50. Here, temperature rises again with height because of the ozone layer, which absorbs ultraviolet radiation from the sun. Jet aircraft often cruise near the boundary between these two layers, taking advantage of smooth air and low resistance. At typical cruising altitude, around 11 kilometers, the air pressure is only 1/4 of what it is at sea level. Oxygen levels are too low for humans to breathe unaided. Airplane cabins are therefore pressurized, maintaining an internal atmosphere equivalent to roughly 2,000 meters above sea level. This system allows passengers and crew to live comfortably in a region where life would otherwise be impossible. Air density decreases with height, and that change affects lift, thrust, and drag. In thinner air, wings produce less lift at a given speed, and engines generate less power. To compensate, airplanes travel faster, allowing sufficient airflow over the wings. The balance of forces remains the same, but the numbers change with altitude. At these heights, winds often follow steady global patterns known as jet streams. Jet streams are narrow bands of fast-moving air, thousands of kilometers long, that flow from west to east. They form where warm, tropical air meets cold polar air, creating strong horizontal temperature differences. Speeds can exceed 300 kilometers per hour. Pilots and flight planners use jet streams to their advantage. Eastbound flights often follow them, reducing fuel use and travel time. westbound flights usually take routes that avoid their strongest currents. Even a small change in altitude or heading can alter flight time by significant minutes or hours. Not all air is smooth. Turbulence occurs when layers of air move at different speeds or directions. It can be caused by mountain waves, thunderstorms, or shifts in temperature between air masses. Most turbulence is light or moderate, a gentle vibration caused by natural mixing of air. Pilots detect it with radar and reports from other aircraft, adjusting altitude to find calmer layers. Turbulence feels dramatic to passengers but rarely poses danger to modern aircraft. Wings and structures are designed to withstand far greater forces. In most cases, the motion is only a visible reminder of the atmosphere's constant movement, the living breath of the planet. Temperature also changes flight performance. In warm conditions, air expands and becomes less dense, reducing lift. At high-altitude airports and hot climates, airplanes require longer runways for takeoff. Cold air, by contrast, is denser, improving lift and engine efficiency. Every flight plan accounts for these variations. Moisture in the air affects performance as well. Humid air is lighter than dry air, since water vapor is less dense than nitrogen and oxygen. The difference may seem small, but for large aircraft, even minor shifts in air composition can influence climb rate and fuel burn. At cruising altitude, temperatures drop below -50 degrees Celsius. The air is extremely dry. Jet engines must be designed to tolerate these extremes. The fuel remains liquid under pressure, and components are built to expand and contract safely as temperatures fluctuate during ascent and descent. The atmosphere is not static. It changes with time and solar energy. The rotation of Earth drives large-scale circulation patterns known as the Hadley, Ferrel, and polar cells. These global loops move heat from the equator toward the poles, shaping climate and weather. Every flight, whether short or intercontinental, passes through air that is part of this larger planetary system. Clouds form when air cools enough for water vapor to condense into tiny droplets or ice crystals. Different types of clouds reveal different conditions. Cumulus clouds mark rising warm air and potential turbulence. Stratus clouds indicate stable layers. Cirrus clouds, high and thin, drift in the upper troposphere and often signal approaching weather systems. Pilots learn to read these patterns the way sailors read the sea. Storm systems, particularly thunderstorms, are treated with respect. They contain powerful updrafts and downdrafts that can reach speeds of more than 100 kilometers per hour. Inside them, electrical charge separates to create lightning. Radar allows pilots to detect and avoid these systems, steering wide arcs around their most active centers. The safest path is always the one that works with nature, not against it. The atmosphere also influences communication and navigation. Radio waves bend slightly in the ionosphere, a layer of charged particles beginning around 60 kilometers above the surface. Satellite signals, including those used for navigation, must account for these bends to maintain accuracy. The science of flight therefore extends beyond the airplane itself to the physics of the space it moves through. Contrails, the white lines that follow jet aircraft, form when hot exhaust mixes with cold, low-pressure air. The water vapor in the exhaust freezes instantly, creating ice crystals that reflect sunlight. These trails can persist for minutes or hours, depending on humidity and wind. They are visible evidence of how the human world interacts with the upper atmosphere. At high altitude, air resistance is low, allowing efficient flight, but radiation from the sun is stronger. The ozone layer absorbs much of the ultraviolet light, yet a small fraction still reaches these heights. Aircraft materials and windows are designed to block it, protecting passengers and instruments alike. Every time an airplane flies, it also participates in the planet's energy balance. Jet engines release heat and gases into the upper atmosphere, where they can influence cloud formation and climate. For this reason, engineers and scientists study ways to reduce emissions and improve efficiency. The future of flight depends not only on physics, but also on responsibility toward the environment that supports it. Understanding the atmosphere reveals how interconnected flight is with everything else. The same winds that carry aircraft also move weather, distribute seeds, and shape landscapes. Airplanes follow these currents like fish in a vast, invisible sea. The sky is not empty. It is dynamic, structured, and alive. The study of flight is therefore also the study of air itself, its pressure, motion, and energy. Every climb through the clouds is a journey through the layers of our own world. In the next and final part of this story, attention turns to the legacy of flight, how aviation connects people, shapes global understanding, and continues to evolve toward cleaner and quieter ways of moving through the sky. For more than a century, flight has transformed the way humanity experiences the world. The airplane changed distance into time, connecting continents that once felt impossibly far apart. It reshaped trade, culture, and understanding. Yet even as it became ordinary, flight has never lost its quiet sense of wonder. Today, tens of thousands of aircraft move through the sky each hour. Each follows invisible paths, airways mapped in 3 dimensions, coordinated by satellites and ground controllers. Together, they form a living network that wraps around the planet. Every journey, from the shortest commuter flight to the longest international route, depends on the same principles first tested by gliders and propellers. Modern airplanes are the result of centuries of refinement. Their wings are sculpted by computer models that simulate every molecule of air. Engines combine strength and efficiency beyond anything imagined in the early days of flight. Materials that were once heavy and rigid are now light and flexible, built from carbon fibers that can withstand extremes of heat and pressure. Each new generation of aircraft improves not by breaking the laws of physics, but by understanding them more deeply. Engineers study airflow at microscopic scales, designing surfaces that reduce drag almost invisibly. Computer systems monitor the smallest vibrations of engines and wings, adjusting automatically to maintain smooth motion. The future of aviation depends on this constant evolution. Traditional jet engines burn fossil fuels, producing carbon dioxide and water vapor that contribute to climate change. As awareness grows, scientists and designers search for cleaner ways to fly. Some research focuses on sustainable aviation fuels made from plants or waste materials. Others explore hydrogen propulsion, which emits only water when burned. Electric flight, once a dream, is now becoming feasible for smaller aircraft through advances in battery technology. efficiency remains the most immediate path forward. Even small improvements in aerodynamics and flight routing can save vast amounts of fuel across global fleets. Airlines increasingly use artificial intelligence to plan paths that follow favorable winds, minimize drag, and reduce emissions. The same mathematics that once lifted the first gliders now guides entire networks toward sustainability. Noise is another challenge. The roar of engines once symbolized power. Today, engineers seek quiet. New fan designs and engine mounts absorb sound, while landing gear and flaps are shaped to disturb air less violently. In the near future, many aircraft will depart and arrive with only a soft, rolling hum. Flight is also expanding beyond the atmosphere. The same principles of lift and thrust that govern airplanes apply, in altered form, to spacecraft. Winged vehicles, such as spaceplanes, use air for part of their journey and glide home through the upper atmosphere. The boundary between aviation and space exploration grows thinner with every generation of technology. Automation continues to evolve. Modern autopilots and flight management systems can handle nearly all stages of a flight, from climb to descent. Yet human presence remains essential. Pilots interpret subtle cues that no machine fully understands: the feel of wind, the changing tone of engines, the instinct for timing and care. Flight, at its core, is both science and art. The spread of flight has also changed how people see the Earth. From above, cities appear as patterns of light, and continents reveal their shapes. The boundaries that divide countries fade from view. The planet appears unified, fragile, and blue against the dark. In this sense, aviation has not only connected geography, but also expanded perspective. Every flight is part of a larger cycle. The fuel burned in one journey contributes to the atmosphere that supports the next. The materials used in construction must be produced, transported, and eventually replaced. Aviation engineers now design with these full life cycles in mind, recycling metals, reducing waste, and planning for energy that renews itself. The idea of flight remains symbolic. It represents human curiosity, the willingness to look upward and imagine. The same impulse that drove inventors to build gliders from wood and canvas now drives scientists to study hydrogen cells and composite wings. Each discovery builds on the last, sustained by the same simple desire to move through air with grace. Across history, flight has required both courage and humility. The courage to attempt what once seemed impossible, and the humility to respect the forces of nature that make it possible. Every airplane, no matter how advanced, still depends entirely on air, gravity, and balance, elements as old as the planet itself. The balance of flight mirrors the balance of life. Lift must equal weight. Thrust must equal drag. Progress depends on harmony, not dominance. When one force overcomes the others, motion changes. When they are equal, stability appears. In this way, the airplane is a quiet metaphor for human endeavor, a reminder that strength often lies in equilibrium. Education in aeronautics continues to evolve as well. Students study not only the mechanics of flight, but also meteorology, environmental science, and data modeling. Flight simulators recreate every sensation of air and movement, allowing new pilots to train safely while conserving fuel and resources. Each generation inherits both the knowledge and the responsibility of those who came before. some of the most promising research in aviation looks to nature for answers. Birds, bats, and insects have perfected efficient flight over millions of years. Their wings flex, twist, and adapt in ways machines have only begun to imitate. Engineers study these mechanisms to design morphing wings, structures that change shape in flight to adjust lift and drag dynamically. The airplane of the future may move less like a machine and more like a living creature. The next century of flight may look very different from the first. Electric and hydrogen-powered aircraft will connect regional cities quietly and without emissions. Drones and autonomous vehicles will carry goods and medical supplies to remote areas. Supersonic and hypersonic aircraft may return, designed with materials that withstand the heat of high speed while using fuel responsibly. Each of these advances depends on the same foundation of knowledge: how air flows, how pressure changes, and how lift supports motion. The science that began with the first curved wing still guides every innovation. Flight remains an extension of natural law, not a defiance of it. Despite its complexity, the essence of flight is simple. Airplanes move by balancing forces that exist everywhere in the world, forces that act on leaves, on birds, and on clouds. To fly is to work within those laws, to trust the invisible architecture of the sky. As the technology of flight continues to improve, its meaning remains constant. Each ascent carries a moment of perspective. The world beneath, vast and interconnected. The sky above, endless and calm. Flight reminds humanity of its capacity to learn and to adapt, to reach upward while staying grounded in understanding. The story of flight is still being written. It began with curiosity, grew through science, and now looks toward sustainability. It is the story of a species learning to move through the air responsibly, guided by the same natural laws that shaped the wings of birds and the winds of the planet. Every airplane that rises into the sky carries that story forward. The long arc of discovery, ingenuity, and care that connects the first wooden glider to the quiet, efficient aircraft of tomorrow. Flight is one of the clearest expressions of human potential, the ability to understand nature deeply enough to become part of it. The airplane does not escape gravity. It cooperates with it, finding balance between pull and lift, motion and stillness. In that balance lies both the science and the beauty of flight, a reminder that knowledge, when combined with respect for the world, can turn the invisible into something graceful, enduring, and free. Inside the body of an airliner, systems weave together like a quiet circulatory network. Electricity from generators on the engines flows through buses and transformers, feeding avionics, lights, pumps, and screens. Hydraulic systems move control surfaces with steady force, turning pilot inputs into precise deflections of ailerons, elevators, and rudders. Pneumatics supply air for engine starts and anti-ice, while air conditioning packs cool and pressurize the cabin. Redundancy sits behind every function, with independent channels ready to take over if one path falters. When power demands change, automatic load shedding protects essentials first. Vital instruments draw from multiple sources, and batteries bridge short gaps so displays never go dark. Quiet logic supervisors compare sensors and vote on the best data stream, guarding against a single faulty reading. The result is a living architecture that anticipates imperfections and continues to operate smoothly. Pressurization holds a gentle interior altitude while the aircraft cruises high above weather. Outside, the air is thin and frigid. Inside, outflow valves and pressure controllers modulate the flow so ears adjust gradually. Oxygen systems stand ready, with masks that deploy automatically if pressure falls too quickly. Engineers design cabin altitudes to reduce fatigue, and humidification strategies on newer types protect throats and eyes on long flights. Temperature control balances multiple zones. Sensors read cabin and skin temperatures, mixing hot bleed air with chilled air from the packs to keep the environment stable. Under the floor, cargo holds receive controlled heating, so live animals and sensitive goods remain safe. Every degree is considered, because comfort supports calm, and calm supports safety. Navigation integrates several independent minds. Inertial reference units track motion by measuring accelerations, dead reckoning through space with no external signal. Satellite receivers refine this picture with updates from multiple constellations, producing coordinates accurate to meters. Radio navigation still adds resilience, with beacons on the ground that confirm position when skies grow crowded or signals degrade. Communication remains layered. VHF radios link aircraft and controllers across busy airspace. HF sets reach over oceans where towers do not stand. Data link messages quietly exchange clearances and route changes, reducing voice congestion and transcription errors. A steady rhythm of contact and confirmation turns the sky into an orderly commons. Protection systems watch the edges. Stall warning logic listens for angles that grow too steep for smooth flow. Wind shear detection compares energy trends on approach, advising a go-around when a sudden loss threatens lift. Ground proximity warning computes a safe envelope around terrain and descent paths, and alerts when the envelope is crossed. Ice detection, fire loops, and smoke sensors complete the shield. Maintenance health monitoring streams data from engines and systems to analysts on the ground. Small anomalies become early signals rather than surprises. Components are swapped before failure, and software updates refine behavior across fleets. Airplanes learn, and fleets improve, one flight at a time. On the ground, an airport is a choreography of timing, weight, and weather. Runways are oriented to prevailing winds and separated from taxiways so movements remain predictable. Grooved concrete channels away water for grip, and lighting patterns describe thresholds, center lines, and approach paths in any visibility. Signs and paint guide pilots like a language written on pavement. Before pushback, weight and balance specialists compute how mass is distributed. Fuel fills wings to reduce bending loads. Cargo and baggage are arranged so the center of gravity stays within limits. A balanced aircraft handles predictably, rotates at the right speed, and flares with grace. Ground power units hum quietly as avionics wake without using jet fuel. Conditioned air keeps the cabin temperate while engines rest. Tugs attach to the nose gear and push the aircraft precisely to taxi lines. When the beacon lights spin, movement begins, and the ramp crew steps clear with a final salute. Dicing is a seasonal ritual in cold climates. Trucks supply heated glycol solutions that melt contamination and leave protective layers. Clear wings support lift. Contaminated wings do not. Timing matters, so crews track holdover time. the window during which protection remains effective in active precipitation. Air traffic control on the surface works like a patient conductor. Ground controllers clear aircraft along defined taxi routes, sequencing departures by wake turbulence category and runway intersection. Tower controllers own the final seconds before flight and the first seconds after landing, handing traffic to departure and approach as the journey continues. Across the field, maintenance bays carry a different tempo. Mechanics inspect fan blades for nicks, borescope turbines for heat wear, and test hydraulic pressures after line changes. Non-destructive inspections scan metal and composite skins for hidden stress. Logs record every action, tying cause to effect so future technicians understand why decisions were made. Turnarounds compress many tasks into minutes. Catering restocks, cleaners reset cabins, fueling completes a computed target with margin for diversions, and water services refresh potable supplies. Flight crews compare weather and notices that may alter routes, while dispatch evaluates winds aloft and alternates for contingencies. The gate becomes a small ecosystem that prepares a complex machine for another arc through the sky. Runway performance calculations consider temperature, pressure, runway slope, contamination, and obstacles. From these inputs come critical speeds and thrust settings that provide the needed climb gradient. Performance is never assumed. It is calculated, confirmed, and then flown with discipline. Flight is physical for every traveler. Circadian rhythms shift when time zones slip beneath the wings, and carefully timed light, food, and rest help the body adapt. Hydration matters at cruise altitudes where cabin air is dry, and gentle stretching keeps circulation steady. Seat design, airflow, and lighting work together to settle the cabin into quiet routine. For crews, fatigue management is a formal science. Duty time limits, controlled rest policies, and roster planning protect alertness. Briefings assign roles, challenge assumptions, and build a shared picture of intent. When turbulence arrives or a reroute appears, coordination is already in place. Above the clouds, radiation levels increase slightly compared with sea level. Shielding in structure and windows reduces exposure, and flight planning avoids solar events when forecasts advise. Sensitive instruments are hardened, and data is checked with parity and redundancy so single-bit errors do not become decisions. Human factors reach beyond physiology into cockpit design. Controls share consistent shapes and movement directions. Critical switches resist accidental contact. Alerts follow a graded philosophy, from caution to warning, with distinct tones and colors. Checklists replace memory at the moments when stress can narrow focus, and standard calls keep teams aligned. Security builds in layers from curb to cabin. Baggage screening, access control, and background checks protect the sterile side of terminals. On board, reinforced doors, discrete procedures, and trained crew mitigate rare disruptions without drama. The intent is to remove surprises and free attention for safe flight. Sustainability now threads through passenger choices and operational decisions. Lighter service carts save fuel. Single-engine taxi reduces burn without delaying schedules. Continuous descent approaches trade speed for smooth, quiet glides that use less thrust. Many small decisions scale across networks into measurable change. Arrival closes the loop with the same care that opened it. Descent planning considers winds, traffic, and terrain. Energy is managed so speed and altitude taper together, allowing flaps to extend without rush and gear to lower at the right moment. Touchdown is firm enough for traction and gentle enough for comfort. Reversers and brakes share the work, and heat is monitored so components cool within limits. At the gate, doors open to another city, and data from the flight uploads to maintenance and operations. The aircraft rests only briefly. Soon, the cycle will begin again, informed by a little more knowledge than before. In the quiet after landing, the larger meaning of flight lingers. Airplanes connect families and work, science and culture, relief and recovery. They move organs for transplant, firefighters to distant fronts, and researchers to the poles. They carry books, seeds, and instruments that build futures out of possibility. The sky asks for respect, and aviation answers with craft, discipline, and care. Every safe arrival represents the alignment of physics, preparation, and human judgment. Knowledge holds it together, and humility keeps it improving. As fleets grow cleaner and communities grow closer, the promise remains the same. Understand the air, work with it, and the path opens. The wing still earns its lift the way it always has, by guiding flow with shape and angle, by exchanging momentum with grace. What changes is how gently that path is traveled, and how wisely energy is spent. Thank you for listening. May the night be calm, may the mind be light, and may rest come easily. Good night.